Thank you, Dr. Falshire.
Okay, why? That's the first time I've encountered that. Privacy issues? What's the?
Yeah, they want us to have just, and I got to do it myself. Thank you, Dr. Falshire. Oh, okay. Okay. We are live. Yeah, I because it's being recorded and live streamed, I think they just want to make sure that only first name and last initial. Okay, so I think we're ready to go. All right, so we're going to get started. Team F will be introducing Dr. Tarter, and that's Daisy, Ian, and Alex. And then we have Shri, James, and Ethan S. that will be asking the questions. Okay. When you put your questions on the Google Sheet, please let them know who you are. All right, let's get started. Okay, Team F, go right ahead.
Alrighty, SSP would now like to give a warm welcome to Jill Tarter, an extremely influential woman in the field of astronomy and the search for extraterrestrial life. Dr. Tarter has led a life dedicated to exploring and understanding the unknown, especially in regards to that age-old question, are we alone in the universe? Dr. Tarter is well known for her work as the director of the SETI Institute on Project Phoenix, a massive decade-long search for aliens in around 750 star systems using telescopes from all over the world. She even coined the term brown dwarf in her PhD thesis. She has won numerous accolades both for her work as a scientist and her work in science outreach, such as the Carl Sagan Prize for Science Popularization and the Lifetime Achievement Award for Women in Aerospace. In the spirit of SSP, she also has an asteroid named after her, 74824 Tarter. Fans of the movie Contact would appreciate that the protagonist, played by Jodie Foster, was actually inspired by Dr. Tarter herself. Project Phoenix began when NASA discontinued its own SETI program and was one of the most ambitious projects of its time. Project Phoenix utilized data from the biggest radio telescopes of the day and combined massive amounts of signals together to analyze distant worlds. Thanks to her charismatic personality, she secured extra funding for those projects, which otherwise may have fizzled out. Ultimately, Project Phoenix succeeded in its observing goals and surveyed hundreds of nearby stars, though it was not able to detect any signs of extraterrestrial life.
However, Dr. Tarter's work didn't stop with Project Phoenix. And before Project Phoenix, she had always played a pivotal role in outreach and private fundraising. And when funding for the SETI program was terminated, she continued to play a leadership role in securing private funding. And since her time at Project Phoenix, she has continued to play a huge role in the technical radio astronomy aspect of SETI, as well as securing crucial funding to keep SETI projects going. For instance, Dr. Tarter joined the management board for the Allen Telescope Array, which is an array of 356-meter antennas at the Hat Creek Radio Observatory. And this observatory simultaneously surveys the radio universe for known and unexpected sources of astrophysical emissions. And it has increased the speed and spectral range for the search for radio emissions from other distant technologies by orders of magnitude. And this was the first or the biggest site that was dedicated to SETI searches from the beginning. And from her work, she has received 2 public server medals from NASA, Time Magazine's 100 Most Influential in 2004, Time Magazine's 25 Most Influential in Space in 2012, and much more.
In addition to her numerous scientific and leadership accolades, Dr. Tarter has focused much of her time on educating the next generation of scientists. Many of her SETI videos have been viewed on platforms like YouTube hundreds of thousands and sometimes even millions of times. She has also worked for many years with major educational institutions. For instance, she served as president of the California Academy of Sciences and continues to serve as a board member. She's also worked as an adjunct professor at USC for astronomy and has created several curricula for teaching everyone from elementary to high school students about science. As we know, quality teaching is a key component for engaging the next generation of STEM students. So we applaud Dr. Tarter for her research and for her dedication to expanding the hearts and minds of students like us through her incredible passion for and devotion to research and science. So without further ado, SSP welcomes Dr. Tarter.
Wow, thank you guys. That was a great introduction. So I can skip my first slide, which is going to be how I would introduce myself. So I would say that I work with teams that use telescopes to find extraterrestrial technology. And I'm the one that's not wearing the headphones. So I have degrees in engineering physics and a PhD in astrophysics. And my jobs have always been about SETI. So I'm retired officially, but I'm still cheerleading for this scientific exploration because I think it's so important. And I'm really pleased to be able to talk with you guys today. In the past, I've been able to do that in person, but this is a different year. So we're going to be Zooming this talk. And before we start, or I start talking about finding them, I'd like to put us into context. Where are we and when are we, right? Well, we're here, obviously. And for me, here is lockdown. Well, no longer lockdown, but still working from home. And that home is here in the Berkeley Hills, in the San Francisco Bay Area. And from the altitude of low Earth orbit, we'd understand that here was on the west coast of the United States. And in 1968, when astronaut Bill Anders took this Christmas Eve photo of Earthrise, we've been able to envision ourselves as being here. This was the first opportunity for a truly cosmic perspective. And I hope by the end of our time together today, maybe I will have been able to help shift your own perspectives to a slightly more cosmic one. And in the summer of 2013, we sent out a memo and said, go out on the lawn and wave, because we took a selfie of Earth with the Cassini spacecraft in orbit around Saturn. And so the end of that arrow, there actually is a tiny white dot. That's us. That's all of us. That's Earth. Long before the Voyager, in 1990, long before Cassini in 1990, the Voyager 1 spacecraft, which was heading out of the solar system, turned around and took this image of us, this pale blue dot caught in a streak of sunlight and dust here. And we now understand that our sun is one of maybe 400 billion stars in something we call the Milky Way galaxy, which is this beautiful grand design spiral. And while everything I've shown you up until here has been an actual image, this is not an image of the Milky Way because we can't get outside of it to look back and take that image. It's an image of a galaxy called M101, which we have long thought is what the Milky Way would look like if we could do that trick of getting outside to take that image. And while we can't do that in optical wavelengths, something like 5,000 hours of telescope time, including the VLA, observing methanol and CO gases in the galaxy has allowed us to actually map the galaxy from the inside out. And indeed, it is fairly similar to what we had thought it would look like. So radio waves travel through interstellar medium without being badly scattered or absorbed by the dust between the stars. And that allows us, with a lot of telescope time, to make this image, which was just published last year. So we're here, right, on one of the spurs of the spiral arms. And indeed, our galaxy is here. This is a piece of the Hubble Deep Field, which was blank until the Hubble Space Telescope spent hundreds of hours imaging that small region of the sky. And you can notice that each of these dots is a galaxy, not a star. And those galaxies all have hundreds of billions of stars. But you notice that some of them are smaller and fainter than others. And that's simply the tyranny of light speed. So these galaxies that are smaller and fainter are farther away, and we, by imaging them, are looking back in time, right? So what do we mean by now, right? Well, now is 13.8 billion years after the origin of the cosmos, right? And we have this incredible scientific creation myth, if you wish, that we have puzzled out by using observations at all kinds of different wavelengths. And we think we fairly well understand the evolution of our cosmos. However, we've only actually seen 4% of the matter energy density of the universe. That's all we've ever been able to detect. We call the rest that we haven't seen dark matter and dark energy. Dark just means we haven't a clue really what those entities are. But as we go back in time towards the very first instance of the existence of our cosmos, we actually have a problem, and we can't make cosmology and gravity play nice. So there is, at the earliest moments, the highest densities and highest temperatures of the universe, there is a lot of work to be done theoretically to understand how gravity works in this whole picture. And so this is the best that we've ever done, this scientific creation myth, but you can expect that our understanding of here and now will change over time as we understand more about the earliest moments. So what about humans? Well, we humans trace our lineage not just back through the centuries of our families, and not just back through the millennia of civilization with its arts and many experiments in governance. We trace our lineage not just back over the millions of years since we branched off from the great apes, and not just back over the 2.4 billion years during which the Earth's atmosphere has been perfused with oxygen, thanks to the photosynthetic labors of these cyanobacteria, blue-green algae. And we trace our lineage not just back 4.6 billion years ago to the formation of the sun and our solar system. We need to go back millions of years earlier to a giant molecular cloud that was contaminated by the winds of Wolf-Rayet stars and the debris of supernovae explosions, a modern example of which I'm showing you here. Because everything that makes you, right, was cooked up in the cores of massive stars that exploded and seeded this giant molecular cloud with the atomic species that would be needed to make the molecules, such as the hemoglobin in your blood. The iron came from this supernova explosion. And we're now seeing that collisions of neutron stars, very dense end products of stellar evolution with one another, can explain the formation of gold and platinum and other very rare atoms minerals that that we use today. So seriously, one of the things that 400 years of scientific exploration has shown us is that it literally takes a cosmos to make a human, right? And you owe all that you are and everything that you see around you to this nucleosynthesis in the cores of massive stars that ended their lives billions of years ago. So it's literally true what Carl Sagan used to say, that we are in fact made of stardust. And so might anything else and anyone else out there be. So we have this science that we call astrobiology, and it's trying to think about and in fact try and detect life beyond Earth. And it does so by looking for two different things. It looks for biosignatures and it looks for technosignatures. And these are perhaps observables that are the result of the actions of life on inhabited worlds. So we're looking for life beyond Earth, and we can do a number of things. We could discover it. We could go there within our solar system to various bodies and find biomarkers. We could look for artifacts in the solar system. They've been here and left us a greeting card. Or we could look for remote biosignatures. And that biosignatures that we're talking about, there's no real smoking gun. But what we're trying to do is build instruments that will eventually be able to analyze the atmospheres of distant exoplanets. And then we're going to look at the chemistry that's going on in those atmospheres. And you can see from that inset in the left corner that the Earth's atmosphere is distinctly different than the atmospheres on other planets. And it has all of these chemical fingerprints of different molecules that are produced by biology on the surface of that planet. So we're looking for disequilibrium chemistry. So in our atmosphere, the Earth's atmosphere, there's methane gas and molecular oxygen. And those two gases, if you put them together in a laboratory, will turn into carbon dioxide and water. And of course, that's happening all the time in our atmosphere. But we have such a strong biological source function for those gases on the surface of the planet that's always replenishing the gases that combine in the atmosphere. So we have oxygen from all kinds of photosynthetic producers on the surface. And we have methane being produced by, among other things, cow farts. So those disequilibrium chemistry components mark our planet as having a very robust biological presence on the surface. And so astronomers and astrobiologists are scratching their heads and trying to think about planets orbiting different stars, different spectral types, different temperatures, different distances, and think about what molecules we should be looking for as a disequilibrium chemistry that might indicate biology on the surface. And it's hard enough to do this on the Earth, and any detection is not necessarily unambiguous. Recently, we've had this conundrum of phosphine gas being detected in the clouds of Venus. Well, on Earth, the only time we find phosphine is in connection with some kind of biological process. And so the authors of this discovery paper went through and they said they did an exhaustive analysis of all the possible chemical networks that could produce phosphine. And their claim was that there's so much phosphine that they can't make it any way without biological assistance. So this is pretty amazing claim this past year that perhaps there's some clues that there is some kind of biology in the cloud layers of Venus, and quite controversial. First of all, maybe it really isn't phosphine because the discoverers had only one single chemical fingerprint to identify the molecule, and perhaps it's been misidentified. We usually like to have dozens of fingerprints to specify a particular molecule. And also, I think we might be a bit presumptive in saying that we have exhaustively considered every single possible chemical reaction that might produce phosphine. Maybe there's something that we've overlooked. So we have this ambiguous claim of perhaps seeing some evidence of biology on a planet other than our own. And we will certainly be sending probes and building instruments to continue to explore Venus with this tantalizing question in our minds. So what else can we do? Remote biosignatures, yeah, but they're likely to be, very difficult and ambiguous, as the Venus experiment shows us, and that's right on our back doorstep. So the other thing that we might do to find life beyond Earth is to detect its work product, something that I call technosignatures, or we could serendipitously, with a piece of equipment or telescope that was intended to investigate something else in the astronomical world, might in fact stumble on a large astroengineering megastructure kind of project. So what's a technosignature? Well, a technosignature is something that is engineered, something that nature can't necessarily produce. And of course, searches for technosignatures face the same problems as searches for biosignatures. They have to deal with false positives and the difficulty of conceiving and building instruments to find what we don't yet know. But despite these difficulties, I think this type of research absolutely belongs in the portfolio of searches for life beyond Earth, and it is potentially what will give us unambiguous answers to the question of whether there is life beyond Earth. So if you're looking for technosignatures, what might you be looking for? Well, I think there are two kinds of deliberate signals that might be manufactured by distant technology. They might make something that looks almost natural, so that when emerging technologies such as ours here on Earth begin to wake up and study their universe with different kinds of tools, they will naturally collect this information And after significant analysis of the data that have been collected, they might come to conclude, that's not right. So what might be almost natural? How about a pulsar? A rotating neutron star whose axis of rotation and the axis of its magnetic field are misaligned. And so as it rotates, it produces a pulse of radio emission when we get into the beam. All right, so a pulsar that pulses at one period and then changes its period. And we've seen that happen because the neutron stars can have star quakes that change their moment of inertia, but we've never seen a pulsar that goes from one period to a second period and back to the first, right? So our searches for pulsars would in fact find such cases if they exist. And we would then be scratching our heads and thinking, maybe that's engineered and not natural. All right, another example. We've been finding exoplanets in transit in front of their stars. And the IAU has made it part of the definition of a planet that it is a spherical body, and the sphere has been formed by its own gravitational forces. So a spherical body passing in front of a star will cast a shadow that is round. But you could imagine an advanced technology engineering, creating, manufacturing, constructing something that orbits around its star that isn't spherical. And as you look at the transit, particularly as the transit starts at ingress or ends at egress, you could find in the higher moments of the light curve, you could find information that would distinguish from a round shadow from something that looked like Venetian blinds or a triangle. So this is an almost natural technosignature that you could capture when you begin to study exoplanets and search for them. All right, here's another example. There are variable stars on the sky. Often Cepheid variables are an example. They have a very accurate period. The star expands and gets brighter and then collapses and gets dimmer, right? Very, very accurate period for these things. Well, suppose you're an advanced technology and you build a orbital neutrino factory, and then you go fly to one of these Cepheid variables, and you wait until the star has contracted and is thinking about expanding again, but hasn't quite gotten the trigger to do so. Well, if you zap it with energy, you can cause it to expand prematurely. And now what you've done is create a second, shorter period. So the regular period and a short period, a dash and a dot, you've got an interstellar Morse code that in fact can be seen all the way to the nearest cluster of galaxies, the Virgo cluster. So that's an example. And how about things that are not almost natural? How about things that are obviously engineered? What might those be? Well, in the radio, we're looking for signals that are compressed to essentially one channel on the radio dial. So the emission or absorption on the radio frequencies is much more confined than nature can arrange. And then we're also looking for compression in the time domain. We're looking for short, bright pulses that, again, we don't think nature can produce. And finally, we're looking, particularly in the infrared, for, for single frequency, monochromatic laser beams that might be employed by an advanced technology to, for example, accelerate a light sail to near light speed. So those are some of the examples of the kinds of things that we're looking for. And why do I make this distinction between almost natural and obviously engineered? It's because for the almost natural signals, what you need to do is astronomy. With every new wavelength for which you invent a detector, and in every single way that you can, look at the cosmos in different ways, and as part of doing astronomy, be aware of these, oh, what was that kind of events? And then for the obviously engineered, you need to conduct systematic searches, but you're going to have to build your own telescopes and detectors because the astronomers won't provide those tools for you because you're looking for things that nature cannot do. So that's why I make this distinction. So SETI was a NASA project for a couple of decades. It started at workshops at NASA Ames, and there we actually split off working groups to think about how you would find exoplanets. Because when NASA got into this game, we knew of only 9 planets within our own solar system. And subsequently, we lost one of those, but we have gained thousands of exoplanets thanks to the work that got started in our SETI workshops, asking the question, how would you detect planets orbiting another star? Published a big, thick conference report called SP419. NASA SETI was also awarded a Golden Fleece by Senator Proxmire. And on Columbus Day in 1992, we launched the High Resolution Microwave Survey, which was to be a 10-year survey looking across the radio spectrum in what we call the terrestrial microwave window. So a range of frequencies roughly from 1 to 10 gigahertz, 1 to 10 billion hertz. So at frequencies that are lower than 1 gigahertz, you have a lot of background noise from the galaxy, from synchrotron radiation, from electrons spinning around the magnetic fields of the Milky Way galaxy. And at frequencies much above 10 gigahertz, you have a lot of noise from the Earth's atmosphere, from water vapor and oxygen. So 1 to 10, cosmic microwave background. The cosmic microwave window is what we wanted to search for 1,000 or more stars over 10 years. And almost to the day after we launched that search, Project Phoenix was terminated. The High Resolution Microwave Survey was terminated by Senator Bryan from Nevada. And he did it with such malice, telling NASA, look, if you come back with this again next year in your budget, your agency won't fare very well at all. So we then sat down at the SETI Institute, which we had chartered in 1984 as a nonprofit. And we sat around reading all of the books about how to raise money. And we just read the last chapter, which was how to raise a lot of money. We didn't have the luxury or the time to think about building a pyramid of donors, a lot of small donors, and eventually you get to the top of the pyramid with a few high net worth individuals that you can approach for funding. We just read that last chapter and created Project Phoenix, which was rising from the ashes of congressional termination. We got agreements that we could still have the telescope time that the High Resolution Microwave Survey had been planning on using. And we got transfer of equipment from NASA to other agencies that was being built for the high resolution microwave survey. And we carried on. And we did observe for the next decade, conducting most of what we would have done with NASA. We lost one element, that is, the high resolution microwave survey was intended to be a two-component search. One would target nearby stars, which we thought might be good hosts for exoplanet life, and the other would make no assumptions about where ET might be, and it would search the entire sky, the sky survey. The sky survey, part of it was being done by the Jet Propulsion Lab, and it used DSN, Deep Space Network Tracking Telescopes, and there was no way after the termination that we could still have access to that. So we lost the sky survey, but we continued with Project Phoenix, our targeted search. And then we sat down about the turn of the century and said, okay, what more should we be doing for SETI for the next 20 years? Let's make a plan. So the results of all the workshops that we held, because that's a standard thing you do when you're starting to try a new exploration, is you hold workshops and bring in all the people you can think of and all the ideas that might not be resident in your own group. And so we published this big, thick book called SETI 2020, and it had 3 recommendations. It said we should expand the wavelength coverage for the search into the optical and infrared. That is, don't just stick to radio. There are good arguments to be made for optical and infrared searches. It also said that instead of begging time on the world's largest telescopes and getting, I think we had 5% of the Arecibo time for years. They said you really want a dedicated telescope so that you can be on the air 24/7. That was the second recommendation. And the third recommendation is that until then, we'd had essentially no sensitivity to short transient events, right? They had to stick around. In our case, with Project Phoenix, we did our signal processing in near real time. And that meant that the signal had to persist for at least a half an hour so that when we went back to check it out, it was still there. But with many other projects that were being done where the data were recorded in real time and analyzed after the fact, and then if something interesting showed up, you'd go back and reobserve. That meant the signal had to stick around for weeks or months or sometimes years in order to be confirmed when you reobserved it. But that meant that we really didn't have sensitivity to transients. So the way to get that was to figure out how to build a telescope that was on the air all the time and looking at all the sky all the time, so that when something went blip over here, you were actually looking over here at the right time to find it. So that's what we took as our marching orders for the 21st century. And I actually had some slides on funding in here, which I removed because I didn't know that you'd be so interested in the roller coaster of our funding history. But here is building a dedicated telescope, right? This is the Allen telescope array, which we had hoped would grow to 350 dishes. But in fact, although we thought we'd done all the technology development that was necessary, when we actually started to build this array in Northern California near Mount Lassen at the Half Creek Radio Observatory, there was so much technology yet to be proven and just invented that we ran out of money long before we got to 350. So if you have to stop short of 350, seems like 42, right? The answer to life, the universe, and everything was a good number to stop at. And that's what we have. We have 42 6-meter dishes, right? And they were designed from the beginning to do radio astronomy and SETI commensally, that is, at the same time. And they have a very, very wide bandwidth receiver that covers the whole terrestrial microwave window from 1 to 10 gigahertz. And because they are small, so we're building a telescope for the first time as a large number of small dishes. Because they are small, they have a large field of view on the sky. And to make that point a little bit more clearly, the spatial and spectral coverage that this antenna array provides was just totally unprecedented. So here's the Andromeda Galaxy, right? And for scale, you see the the moon as compared to the Andromeda Galaxy. And the beam of the telescope that we built, the ATA, actually encompasses the whole Andromeda Galaxy. So you can see here, the pink is the 2.5 degrees field of view of the Allen telescope array telescopes. And you can see over to the lower left-hand side, you could see what was the field of view of the Arecibo 1,000-foot telescope. And because that's so small, they built instruments on it that could have 7 different beams simultaneously on the sky to enlarge the field of view. But now, if you look at the 6-meter telescope, as opposed to a 300-meter telescope, you see the enormous field of view. And we use spectral imaging correlators to make an image in the radio of that entire field of view. So it's like having a radio camera with 1,250 pixels and 1,024 colors or frequency channels. And then you have a wide angle radio camera, had never been done before. And you can, because there are so many baselines, that is, vector pairs between every 2 antennas, you don't have to image for hours to make this picture. You can use all those baselines to make a quick snapshot. And you can also, so for our case, we built a back-end spectrometer correlator that could form three different beams anywhere in that field of view simultaneously. And we used each one of those beams was an off for the other beams, which was one of the things that was important in the way that we do SETI. And we could also create nulls. We could put, as you're getting the voltages from each of those individual telescopes, before you put them together, you can add a weight, and you can set a phase, and you can arrange it so that in a particular direction, there's no sensitivity. You can actually null out the telescope, and in that way, hopefully, be able to block some of our own technology that is creating interference. So we use this on the Allen Telescope Array for a number of years. We started with looking at a catalog that was called HabCat, which we created before any exoplanets were ever detected. We just thought they would be good stars to host exoplanets. And then finally, when we began to find exoplanets, we put those on our target list. And when the statistics eventually told us that essentially every star has a planet, we just said, okay, we're going to start with the stars that are closest to home and reach outwards in distance with a catalog of something like 20,000 nearby stars, which is most of which are red dwarf type stars. And you can see that map. That's an astronomer's look at the sky with two coordinates, declination and right ascension. And you can see there's a big blob sort of at the right hand part of that chart in pretty much the middle of the declinations, right? And that is the Kepler field of view. So we spent a lot of time surveying the Kepler stars, and the rest of the surveying that we've done attempts to cover the rest of the sky. And you can see that there's a blank strip at constant declination across all right ascensions. And that blank strip is where the geosynchronous satellites orbit. You definitely don't want to look at those with very sensitive radio equipment, right? So we avoided the geosync belt. And we finished up this survey, excuse me. In 2020, when we began refurbishing the receivers on the Allen Telescope Array. And there's now a new player in this field, which is wonderful. It is the Breakthrough Listen. Oh, I'm sorry, I forgot that I highlighted the Kepler field and the geosynchronous belt. Breakthrough Listen came online 5 years ago. It's results from a $100 million pledge from a very wealthy individual, Mr. Yuri Milner. So he's pledged $100 million over 10 years. And instead of building their own telescopes, as we have done, Breakthrough Listen is buying time on large telescopes around the world, starting with this 100-meter telescope called the Green Bank Telescope. And Breakthrough Listen is building spectacular back ends, multi-channel spectrum analyzers, if you wish, better than what we were ever able to do with Phoenix because of the incredible improvement in digital technology over the decades. So starting at Green Bank and at Parkes, 60-meter telescope in Australia for the southern sky. And they're also looking in the optical with this telescope, which is called the Automated Planet Finder at Lick Observatory in San Jose in California. And then they are also building back ends now for the large 500-meter telescope that looks like a big Arecibo in China, FAST. They're also working with Meerkat, which is a prototype array of dishes for what will eventually, we hope, become the Square Kilometer Array in South Africa, and then the Jodrell Bank Telescope in the UK, and the Merlin Array, which is associated with it. So that's where Breakthrough Listen is working. There is, in fact, more SETI than just Breakthrough Listen. Breakthrough Listen is the 900-pound gorilla, but there is more SETI going on. First of all, there was SETI at Home, where you could download blocks of data onto your phones or your PC and analyze it in the background. Those data were coming from Arecibo, which unfortunately we no longer have. It suffered a fatal collapse at the end of last year. We don't know what will replace it in the future, but hopefully there will be a replacement. And LOFAR is a series of very low frequency arrays spread around Europe and the UK. And here's one in in Holland, and it's been working in conjunction with a similar telescope in Sweden to do low frequency searches, that is below the bottom of that terrestrial microwave window. There's a group in Italy, in Medicina, which is doing SETI Italia, and back at Goldstone, right? So I did mention that when the project, the high resolution microwave project was terminated, we lost the use of the Deep Space Network telescopes. However, in the meantime, NASA has taken one of those 26-meter telescopes from its Deep Space Network and moved it outside the fence of the Goldstone complex, and has established, in conjunction with local school districts, the Goldstone Apple Valley Radio Telescope, which is being used as a research tool operated by high school students. And those students have resurrected the sky survey plans that we had with JPL, and they are tessellating the sky in a sky survey continuously. So we got not the full sensitivity because it's only one antenna, but in fact, they have resurrected a sky survey. And then there's a project run by a scientist in Japan, which has calls periodically to all optical and radio telescopes observatories, asking them to look at a particular piece of the sky simultaneously at all different wavelengths. So as for optical SETI, here's a telescope built at Harvard by undergraduate students. And it does a sky survey of all of the sky that can be seen from Harvard, Massachusetts, continuously. We've had scientists who have taken data collected at the Keck telescopes in Hawaii, right? Data collected for looking for exoplanets and reanalyzing those data, looking for laser signals. There is an amateur optical SETI observatory down in Panama. And it's also possible to do archival searches. So looking at data collected for other purposes by astronomers, and in this case, looking at the data collected by the infrared satellite WISE, which essentially looked at all of the sky, looking for advanced Kardashev type 2 and type 3 civilizations. So a Kardashev 2 civilization is characterized by its ability to capture all of the power emitted by its host star. And Kardashev 3 is something that can harness all of the power emitted by all the stars in its host galaxy. And Kardashev 1 is, which the Earth is almost getting to be, is able to utilize the power that falls on the surface of its planet from its host star. So literature or archival searches have been done in the infrared, and a lot more can be done as we begin to build up these public databases of vast amounts of data from dedicated observatories. So there are a couple of new optical SETI projects. Veritas has just come on the air in the last year. It is actually a telescope that is looking for radiation from high energy particles entering the atmosphere and producing Cherenkov radiation by interacting with the atoms in the atmosphere. But basically, these telescopes have large format CCDs, or photodetectors to start with, and now CCDs, where they have maybe 900 pixels at the at the focus. And so the folks who want to find Cherenkov radiation are looking at all of those pixels for long streams, air showers. But we, the SETI community, was able to write some new software. And so instead of looking for many pixels lighting up, it looks for an individual pixel on the sky lighting up, and requires to be interesting as a SETI target that same pixel on the same piece of sky light up in all 4 of the telescope detectors simultaneously. So single pixel detection. No new hardware, just new software. One of the new pieces of hardware that's being built is being built by Shelley Wright down in UC San Diego. And you can see Shelley there imaged through a large plastic Fresnel lens. And now imagine building an observatory where you have a hemispherical dome and you put those Fresnel lenses in each of the components of your, essentially it's a Buckminster Fuller construction. And those Fresnel lenses will take a large piece of the sky and image it onto a very efficient photodiode detector. And so at any one moment, you can see with this dome and these lenses, you can see 10,000 square degrees on the sky. And then if you build a second dome that is hundreds or 1,000 meters away, and also have it looking at those 10,000 square degrees, you can look for signals that might be transient, but that are simultaneously observed by these 2 domes. And then you build 2 more in the southern hemisphere, and now you've covered all of the sky, all of the time. So the first prototype instruments have been constructed and were being field tested at Lick when everything shut down, and they're beginning to start up again. And then here's another way to look at all the sky all the time. And it's using not a telescope, but using cameras with very wide angle lenses. And in front of those cameras, you put a grating and you read out the grating very quickly. And you're sensitive to flashes on the sky at optical wavelengths that could be as short as a nanosecond or as long as a few seconds. And it takes, this site that I'm showing you here is in Northern California, and has been installed for about a year. And we have more units that are going to be installed in Haleakala at, well, by the end of the summer. I mean, the pandemic has also put that whole schedule out of whack. But you can see if you have a dozen of these sites around the globe, then it's actually possible to look at all the sky all the time, right? So these are the newest optical SETI projects. And then we have, what about the upcoming astronomical facilities? What could we do with them? Well, we're scratching our heads about the James Webb Space Telescope, which we hope will eventually launch. and trying to think about the data that it will make available and how we could mine that data for optical SETI sources. And then there's a telescope with a sun shield called HABEX in the future, and another large ultraviolet infrared, a large ultraviolet optical infrared telescope, LUVOIR. And these are going to provide massive public data sets. I think we can't, let's just say we haven't had any luck in thinking about putting specific SETI backends onto these orbital platforms, because that's weight, and weight is a lot of money. But we are thinking about how we can use the data that will be made available in the future from these agency spacecraft. Right? There's even a funny plan for something that looks like this. It's kind of a cross between optical telescope, a radio telescope, and an amusement park ride. That's what it always looks like to me, called ExoLife Finder. And this is a very special purpose telescope. It really can only do the job that it's intended to do for the Proxima Centauri system, the closest stars to us. But it's possible, as you track these exoplanets in orbit around these nearest stars, and you get the light curves, and you then add them together and in fact pull out an opacity map for the nearby planets for Proxima b. Discriminating that opacity map will allow you to distinguish the beachfront property from the deserts, if any, on that planet. And so there's a lot of technology development going on right now. It isn't clear until the astronomers finish their decadal review process, which is supposed to publish this summer, whether the community has an appetite for a single purpose telescope. I mean, usually when we build a new facility, we build it with the capability to do all kinds of different science for all kinds of different people. Whether the community will get behind this relatively inexpensive single-purpose ground-based telescope is an open question. And if they don't, the question is this fundable by philanthropic or foundation sources? And we'll be looking at that question. But this would be the first opportunity to actually try and get a surface image of Proxima b or any of the other planets in the system. Okay, so laser SETI I already mentioned. The ground-based 30-meter class telescopes, the TMT, the Gemini telescope, and the European extremely large telescope at 40 meters, which is actually scaled down from something that was called OWL, the overwhelmingly large telescope. This era of telescopes is being constructed right now, and we want to figure out how we can put commensal instrumentation onto these. There's a much better chance that we will succeed with these ground-based facilities rather than the space-based future telescopes, because we don't have to pay such a high price for increasing the weight. The Large Synoptic Survey Telescope will give us a movie of the night sky, all the sky, every 3 days. We talked about laser SETI as a way of looking at all the sky all the time. PanoSETI, again, looking at 10,000 square degrees of the sky at a time. Veritas, which is working today looking for single pixel events in the focal plane detectors. And then FAST, the large radio telescope being built in China, and Meerkat being expanded to the square kilometer array in South Africa. And so we have begun with instrumentation on FAST and the square kilometer array. Breakthrough Listen is doing that. The next generation VLA, which will not just be Socorro, but spread across the west and southwest of the US. And I just bring your attention to look at the geometry of the next generation VLA and the square kilometer array. These are off-axis Gregorian dishes. This is what we pioneered at the Allen Telescope Array. Turns out to be a good idea, and other people are taking advantage of it, which is great. If in fact that ExoLife Finder ever gets built and the technology is demonstrated, then you could imagine building a much larger version of it called Colossus that would actually be able to detect the heat islands from cities or on exoplanets, right? It would be so sensitive that it could do that. It's a long way from getting off the drawing board, and I don't know if it'll ever be built, but we're eager to see what happens. And then the day after tomorrow's telescopes, the square kilometer array, which is 100 times bigger than the Allen Telescope Array and goes to lower frequencies, but not as high in frequency as we had planned. For the ATA, and the high frequency piece of this may in fact turn out to be the next generation VLA. So this telescope would be able to not just have 3 beams the way we did at the Allen Telescope Array, but maybe 250 beams, each one pointed at a different target from the millions of stars that have been identified by the Gaia spacecraft. So 100 times the sensitivity gives you 10 times the distance for any given transmitter. And so you could see a single 1-watt cell phone out to the distance of 1/100th of a light year, a television transmitter out to 6 light years, airport radars out to 100 light years. And if we ever replace the Arecibo 20 terawatt planetary radar, you could see that signal with the square kilometer array out to a distance of 50,000 light years, within which distance there are lots of target stars. All right, so some things don't change. We still fly the flag of Earth whenever we're observing. And we still plan for success, right? There is champagne on ice when the SETI Institute is observing at the Allen Telescope Array. And the other thing that unfortunately is changing is that the radio frequency interference is growing every year from our own technologies. You can see here the frequency bands that were blocked by our technology starting back in 1995 in Parkes, and then moving forward to the Allen Telescope Array, which is in a very quiet site, but nevertheless, we've got bands that are blocked by aircraft transponders and radars and other technologies. So it's getting harder to do this radio search anyway, even at quiet sites. And the same is true for the optical searches, because light pollution is encroaching on what used to be very isolated observatories. So over time, the technologies have changed. So when we started back in 1992 with the high resolution microwave survey, we actually had to build our own chips to do fast Fourier transforms fast enough to allow us to do this near real-time observing. And then the next generation, so the new search system was made with FPGAs. And then when we started working at the Allen Telescope Array, we had a mixture of field programmable gate arrays, I should say, very a hugely dense chip of transistors that you could program various areas to do various jobs. And then at the ATA, it was FPGAs and CPUs, computers. At Sonata, when we started the Sonata SETI on the ATA program, we had a bunch of dedicated CPUs from Dell. They had gotten fast enough, so we didn't need anything except one small accelerator card. And now the Berkeley Breakthrough Listen hardware is based on GPUs, right? And if you can get them, right, because they're so rare right now, because everyone is using them to mine Bitcoin. And so there's a huge shortage of these GPUs and NVIDIA cards. So it's been a long story so far. And when SETI turned 50, I tried to estimate how much of the cosmic haystack have we actually observed, right? So there are 9 dimensions of that haystack: spatial and temporal and polarization and frequency and sensitivity, modulation. And I tried to put an estimate for how big each of those dimensions was, and I just multiplied them together to get a 9-dimensional volume. And I said, okay, I can't do 9-dimensional volumes in my head. Probably you can't either. So let's just take the total volume that SETI might have to search to be successful at finding an electromagnetic signal, assuming that's the right thing to look for, and set that volume equal to all the world's oceans. And how much had be searched? Well, at age 50, we had searched 1 glass out of the oceans. And the students at Penn State more recently have redone the calculation, finding that at age 60, it's more like a small tub, hot tub or pool worth of the oceans. So not yet a lot, but again, our technologies are getting faster and faster, and we can do more searching in the same amount of time than we've been able to do before. So our searches are speeding up, and it's more than just Moore's law, right? Because there have been accelerations in the receiver technology, lower noise temperatures, the different kinds of antennas that are being built. And we are able to on the sky because we've been developing these commensal searches. In fact, I failed to mention that there's a new project called Cosmic that's being done at the SETI Institute and in conjunction with Berkeley, where we are going to be able to take the output of all of the VLA 27 antennas, and we're going to have a different parallel output path so that we can do commensal observing on the VLA all the time and do our own data analysis. The primary observer still decides where to point the telescope and what frequency bands they're using, but we can in fact have access to other frequencies and all of the output from all of the telescopes to do SETI. And so this is one of the things that we're working on right now, in addition to trying to use machine learning to build better detection algorithms. So finally, in this question of life beyond Earth, so we can discover it, we can detect its work products, we can also export it. right? We're talking about going back to the moon. We are talking about colonies on Mars and perhaps mining on asteroids. So we can take life beyond Earth out into the cosmos. And there's talk about how you might build a starship that could support a human colony to travel to the stars, both the 100-Year Starship Study and Project Icarus. So I like to have the opportunity to talk to you students and any audience that I can. I like to really talk about SETI because I hope that it allows me to change your perspective. I hope that thinking about SETI kind of holds up a mirror to all of us on this planet and says, you know, at first blush, there are all kinds of differences. But in reality, in that mirror, we humans are absolutely all the same when compared to someone else that arose and evolved around a different star. And so I think SETI provides us an opportunity to trivialize the differences among humans. And that is incredibly important right now because we on this planet, all life on this planet, faces a number of huge challenges. And those challenges do not respect national boundaries. They are challenges that we are going to have to solve cooperatively, collaboratively, as a global society. And so to the extent that SETI helps us to have this more cosmic perspective, I think it's really important for our long future. And so my last slide comes from Caleb Scharf, who's the chairman of the astrobiology department at Columbia. And Caleb points out that on a finite world, and you see it right there, our finite world, a cosmic perspective isn't a luxury, it's a necessity. So when we finish here, I'd like you to all take on a homework assignment, and that's go to all of your devices where you have digital profiles of yourself and put there the first thing that you say about yourself is that you're an earthling, and then try and act like one, because we need to work on having a long future for us and all the life on this planet. Thank you. And I was expecting you to interrupt me with questions. Did I just not hear them?
I think they were trying to wait till the end, but go right ahead, guys. I think they have some questions for you, Dr. Tarter.
Great.
Hi, so the first question is from Sanjana K, and this is something that I was actually wondering as well. You discussed how we look out to detect signals that may be coming from other life, and are there any ongoing projects to send out signals?
We have done that in the past, but I wouldn't characterize it as ongoing. And in fact, it's a bit of controversy in the field. Some people, Stephen Hawking being one of them, said, you really ought not to shout in the jungle. They'll just come and eat you up. Stephen said, it didn't work out very well for the natives when Columbus showed up. That is, an advanced technology showed up. So there have been stunts. NASA did one as well, of transmitting for a short period of time. And we have a lot of leakage radiation. We have TV broadcast. Even when it's satellite and downlinked, you have a back lobe to that satellite. And we have airport radars and other transmitters on the planet. So we're leaking, we're radio loud. But in terms of deliberate transmissions, there isn't an ongoing program. We have used the meetings of the AAAS, American Association of, what is it? Remind me, American, sorry. Anyway, big scientific body. We've used their meetings to hold sessions about whether we should transmit, and if so, who should speak for Earth and what should we say? And again, controversy that we don't seem to be getting any closer to solving. My own personal opinion is that we're too young. We're such a very young technology in a very old galaxy that we're not yet capable of taking on long-term projects. So if you transmit for 5 minutes, that signal is going to go past any intended target in 5 minutes. And they need to be looking at you at exactly the right way at exactly the right time to detect that signal. So I think that transmission is a long-term project, and that once you start, you don't stop. And I just don't think that we're organized enough, old enough, wise enough to take on a project that could last 10,000 years. So what do you think? Should we be sending signals? So you asked me, now I'm asking you, what do you think? Because you've got a totally different worldview than I have.
Yeah, I mean, I personally, I would think along the same lines. Whenever I've thought about this before, I can only imagine a civilization receiving them, which is much, much more advanced than we are. And that would likely turn out badly for us. So I agree with the sentiment that we aren't really ready for that.
Yeah, I'm also not completely down with the idea that it would turn out badly for us. So if they're going to get here, right, they are more advanced technologically than we are. Therefore, they're presumably older than we are. And I don't know how you end up being an old technological civilization unless you outgrow all of the quarrelsome, aggressive tendencies that probably helped you to become intelligent in the first place. You know, it's along the line of Steven Pinker, who says that once cultural evolution began to take hold, we all became kinder and gentler than we ever were before. So an old technological civilization might not be so aggressive. It might not be like Columbus showing up in the Caribbean. So I don't know.
We have another question from Grant T, who's asking, do you also look for megastructures like Dyson spheres under obviously engineered, like in that category?
We do, but primarily as archival searches. So we don't have, let me think. I'm thinking about the SETI Institute now. Let me think about other. I'm unaware of anyone who has built specific equipment to do such searches in near real time. But we certainly do look at archival data. In particular, there's a star called Boyajian star that was found during, by actually citizen scientists looking at data that was made public by the Kepler spacecraft. And usually when a transit occurs, the light curve of the star dims by a fraction of a percent, right? The citizen scientists found that aperiodically, which is why Kepler's own detections didn't find it, aperiodically, this particular star would dim by as much as 20%. And people were really, really scratching their heads. And all kinds of different observatories around the world at different wavelengths started taking data on this star. And at first, they said, well, it can't be dust because it doesn't have the right spectral index. And then they said, oh, maybe somebody's building some kind of Dyson sphere or megastructure around this star. And when part of the construction comes into view, it blocks some of the light. And the reason it isn't periodic is because the construction is ongoing and things are moving around. So the whole megastructure idea. And eventually got enough data, new data on this star taken by many different observatories, that it was actually possible to fit a spectrum and show that actually it could be dust, clouds of dust that were obscuring the star so heavily. So people, that was Jason Wright in the case of Boyajian star, did that data look. And people are really looking through archival data just to see if they can find some, my goodness, what's that aspect. But I don't know of anyone who's built equipment to look in near real time.
All right, and we have another question from Sonal B. If intelligent forms of life were found, how would we interact with them? Would we develop universal methods of communication, and if so, how?
Yeah, wow. Wish I had an answer to that question. There is a whole sub-discipline called meta law. It's being carried out by places that specialize in space law. And they're asking the ethical and logical questions about how do you interact with an other, right? So yeah, you'd like to say, well, first of all, the golden rule, right? You treat them the way they'd want to be treated, but you may have no idea how they'd want to be treated. So people are puzzling over this, ethicists as well as space lawyers. And it might well be that we detect life beyond Earth by observing information-bearing signals. And it might well be that our communication with them is actually only one way. If you think about the ancient Greeks and Romans and Shakespeare, we learn a lot by reading what they left behind, even though we are incapable of directly asking them questions. So one-way communication might be a reasonable thing to think about. It's also true that if they show up here, they're going to dictate how the interaction goes because their technology will be so much more capable than ours.
All right, thank you.
And our next question is from Joey T. He asked, if you have as much funding as was needed, what would it be used for? Would it be used to complete the rest of the 350 for the ATA 42? Or are there other projects as well that SETI is looking to fund to help with the search for extraterrestrial life?
Well, if there were adequate funding, for to do everything we'd like to do, we certainly would complete the ATA, put it out to 350 telescopes. We would also build an equivalent in the Southern Hemisphere, and we would finish building those optical systems, the PanoSETI and Laser SETI, and deploy them north and south and around the globe. We'd also do something that wasn't done for a very long time, and that's work with university professors to develop curricula on this topic because it is really, really rich with opportunities to provide classes about physics and chemistry and biology and technology and behavioral psychology. So we'd like to re-engage with your generation and the generation coming behind you in a university setting. There are only about 3, let's see. So Penn State, UCLA, Berkeley are the only examples of full-blown SETI curricula that I can think of. But we really would, given the fact that this is likely to be a multi-generational project, we would like to train our successors. And the other thing that I would do with funds is to create an endowment, right? Understanding that this well might be multi-generational, and that we don't have a solution like build this collider and you can detect the Higgs boson. I'd really like to see a stable, going far into the future, funding platform that can encourage the best and the brightest to get involved in these activities. So, you know, when you try and recruit someone to work on SETI, first of all, you have to get over the little green men kind of giggle factor, and you have to explain to them that while they might not succeed in finding a signal during their working career, they will definitely be able to do a great deal of instrument and scientific exploration and build tools that will allow the search to be better tomorrow than it is today. And if that is something that gives them a reward, then they should join us. But if you then also have to say, oh, and by the way, funding for this has been kind of sketchy over the decades, and I can't promise that I can make your salary next month. That's really hard recruiting, right? So if you have an endowment that provides an adequate level of funding year upon year, then you have a much better opportunity to attract the best minds and the cleverest people to work with you.
The next question is another one from Grant, who asks, has space junk ever caused issues with the search for extraterrestrial life?
Yes. So first of all, the direct transmissions, right, from orbiting spacecraft down to Earth, right? You saw in that one slide that we avoid the geosynchronous belt because it's so loud you can't hear anything through it. In terms of space junk, yeah, it has, and that's harder to show, but we have actually done some studies where transmission from something in a higher orbit will reflect off some junk in a lower orbit and give you a detectable signal at the telescope. It's usually something that you can rule out because it doesn't persist, right? But yeah, there's a problem.
Okay, this next question is from Hidam I, and it's, may you please explain how the opacity map is made from data and how the data is analyzed and what it can show?
Okay. Well, I should have put some more slides in then for that. Think about a planet that's orbiting around a star, and it has one big continent, right, in the middle of all oceans. As the planet rotates and as it orbits around the star, position of that ocean is going to change. And when the position of that island or rock is going to change. And when it's on the far side from you, the star will be its brightest. Right? So now if you observe that star and get its light curve, the amount of light from that exoplanet throughout its orbital period, and many, many periods, you can in fact deconvolve those light curves and figure out that you've got a bright planet, bright exoplanet with one dark patch. And I think that's an easy case to visualize in your head. But then when you have multiple continents and oceans, the deconvolution takes more orbits of data and is more difficult and is maybe not in the end unique. There could be multiple solutions, but you can then begin to think about how that might work. So essentially you're looking at the planet from lots of different angles over time and just measuring how much light is reflected off that planet.
Great, thank you.
Did that help? Or I can keep trying to work on it for you.
Yeah, I mean, it helped me. I'm not sure. You can ask the person who asked that question too, but
Thank
yeah, it
you.
makes sense to
I
me.
understood. Yeah. Thank you.
Okay.
The next few questions by Morgan J, Alex Y, and Andrew L are asking pretty much the same thing, which is when or if we do eventually find an advanced civilization, what are the implications for human life on Earth? Should we make contact? And what are the next steps we should take from there?
Yeah, well, back in the 1980s, right, dark ages, very middle of the Cold War with the Soviet Union, former Soviet Union, we would have meetings every October under the auspices of the International Academy of Astronautics that has had a permanent SETI committee, standing committee for many decades. And back in the 80s, in these committees that met every October, we set out to write a bunch of protocols. In fact, since the International Institute of Space Law was also co-involved, it got this name called Principles Concerning Activities Following the Detection of Extraterrestrial Technology. And we worked on this because it was a good thing to do, but also because we wanted to give our Soviet colleagues some backing, because we were afraid, and they were afraid, that if they ever succeeded, they wouldn't be able to announce their detection. So the protocols just have a number of common sense aspects. One, check it out. Make sure, using equipment at your observatory, that it's real and it isn't an artifact of data analysis or some sort of interference at your telescope. And the best way to check out the interference, local interference, is to quietly call up a telescope to the west that has the frequency capability and ask to see, tell them that you'd like to see if they can verify what you're seeing. So get an independent verification. Hardware you didn't build, software you didn't write. And then the next step is to tell the world. And so we wrote down some guidelines of how do you make sure that everybody who's been involved in the discovery gets appropriate credit. How do you make sure that you get to have this information be announced to the public? And then there was another step that we put in there, which is to say that the people who signed on to this protocol, and there's no legal stature or enforcement to it at all, it's simply a scientific handshake, that those who sign on to these protocols would not transmit a reply until there is some consensus on whether we should and who should speak for Earth and what should they say. Now, we didn't then, nor do we yet, understand the best way to create such a consensus and have these discussions. I mean, we brought these protocols to the UN Committee on the Peaceful Uses of Outer Space, and they said, yes, thank you, and filed them away and have never looked at them since, I'm sure. But we are trying, by having open discussions and looking at some of the collaborations that are going on globally around climate change and the experiments that are being done, we're trying to figure out what is a good vehicle for getting global consensus. And then I'm less worried about who will speak and what they will say. But I would like to think that there was a way, because there's so many other reasons to do so as well, to get global consensus. And once, when Freeman Dyson heard me talking about this, he just chuckled. And he said, Jill, come on, get real. If you ever announce that you've detected a signal and you give the discovery parameters, everybody who has any ability to get hold of any kind of transmitter will do so, and they will just transmit whatever the heck they want to say. This is a losing game. You cannot control that. And then he chuckled again and he said, that cacophony, probably about the best representation of the 20th century Earth that you could have. So, no answer to your question, but I know there should be an answer.
Thank you.
All right, Haydem has another question. Can you please explain the difference in data handling from a radio telescope and a normal photometry for exoplanet transits?
Okay, so when you're doing photometry for exoplanet transits, you never see, you never actually image the planet. All you see is the amount of light that is being reflected, right? So when the exoplanet is in front of its star, is transiting, the total light that you detect is minimal. And when the exoplanet is behind the star, right, you're just getting the stellar light. And on either, when the planet is in its orbit on either side of the star, you have both the starlight and the reflected light from the planet. And so what you do is you try and subtract those spectra. So you try and the difference is the light being reflected from the exoplanet. So you try and subtract out the stellar light. With a radio telescope, first of all, stars are not very bright in the radio. And what you do is just, again, you can't distinguish. You can't say, I'm going to point my telescope at the exoplanet because it's so close to its star. They're both in the field of view. And so with the exoplanet and looking for engineered signals, you look to see in a very narrow frequency range how that signal changes over time. We call it a Doppler drift because of the rotation of the Earth, and pointed in a particular direction, and with respect to a particular reference frame, you can actually correct for that. And then the rest, if you have a narrowband signal, the drift will be due to the motion of the exoplanet around its star. And so if you have enough frequency channels and you look for a long enough time, you can actually see that signal drifting.
So
Okay.
how many, real quick, Ethan, how many more questions do we have? Because we do have a learning block at 2 o'clock Mountain Time.
We have 8 more.
Okay, so we're just going to be able to ask maybe one more, so you guys can have a quick break before learning block. So go ahead and pick one. Last question.
Okay. So this question is from Amanda, and she was wondering if you could explain a bit more about LOFAR and if there's any specific advantages of using a lower frequency.
Okay, LOFAR is tiles of essentially dipole receivers, thousands and thousands of them. And we have avoided historically the low frequencies because of the synchrotron radiation background from the galaxy. But having said that, these tiles actually look at most of the sky that's overhead all the time and can therefore map things that are changing on the sky. And the low frequencies give you a bigger field of view. So LOFAR is a very good survey instrument, and it can tell you what's changing on the sky. And when you use 2 of these tiled arrays and you observe in common, you observe simultaneously the pieces of the sky they see that overlap. If you see something in there that's temporally changing, it's a very good verification. You know it's not interference or your equipment.
Okay, thank you. And can I ask one more question? It's my own question.
Yes, go right ahead.
I was just wondering, it's kind of hard to answer this, but in your own personal opinion, how common or rare do you think life is in the universe as a whole?
I don't know the answer to that question.
Yeah.
And if I told you an answer, it wouldn't be science, it would be religion, right? Belief is not the opportune or the operational word here. Exploration is what this is all about. And if we ever find life beyond Earth, then we'll have a better answer to that question. But right now, anything that anyone tells you is just belief. And I'm waiting for the data.
Thank you.
Thank you, Dr. Tarter. I wish we had more time. I really do, because this is so interesting, and I know you guys are also interested. Thank you to our teams today for introducing Dr. Tarter and for fielding the questions. Is there anything else anybody would like to say before we say goodbye to Dr. Tarter? Other than I know that you guys are very thankful that she came today.
Next time in person, hopefully.
Oh, that would be great. Well, we thank you so much for your time today. And all participants, you are able to take a quick break and make sure you're back in learning block at the top of the hour, okay? All right.